Ever pondered about the mysterious connections in the universe that defy our understanding of reality? Enter the intriguing world of quantum entanglement, a phenomenon that seems to laugh in the face of space and time. Imagine a pair of particles, let's call them Alice and Bob, that are entangled in such a way that the state of one instantly influences the state of the other, no matter how vast the void that separates them. Alice could be lounging on a beach in Hawaii while Bob is chilling on the dark side of the moon, and yet a change in Alice's state would immediately reflect on Bob. This isn't just faster than the speed of light, it's instantaneous, defying our everyday understanding that information cannot travel faster than light. But how does this happen? Quantum mechanics tells us that particles exist in a superposition of states until measured. When Alice gets measured, she collapses into a single state, and at the exact same moment, Bob too collapses into a corresponding state. It's as if they had a secret pact, a predetermined script they decided to follow. This leads us to a fundamental question. How do Alice and Bob communicate across vast distances to coordinate their states? Some physicists propose hidden variables or mysterious forms of instantaneous communication, while others argue that Alice and Bob were always connected in a way that transcends our conventional understanding of space and time. As we delve deeper into this paradox, we encounter numerous experiments aimed at shedding light on this bizarre aspect of our universe. These experiments are not just about understanding the nature of reality, but also about harnessing the potential of quantum entanglement for advancements in fields like quantum computing and cryptography. Quantum entanglement is a phenomenon that challenges our everyday understanding of the universe. It opens up a universe of possibilities, a universe that is far stranger and far more connected than we could have ever imagined. The Einstein-Podolsky-Rosen paradox, or EPR paradox, opens a door to a whole new perspective. This paradox, named after the three physicists who proposed it, challenges our conventional understanding of reality. It's an enigma that reveals a startling concept. Measurements on one particle can instantaneously influence the properties of another, regardless of the distance that separates them. Picture two entangled particles, which we'll affectionately name Alice and Bob. When we make a measurement on Alice, her state becomes determined. But here's where things get truly weird. As soon as we measure Alice, Bob's state also changes instantaneously, even if he's light years away. This shatters our everyday understanding of how influence and information travel. Normally, we'd expect these things to move at a finite speed, but in the quantum realm, the rules are different. So how does this strange phenomenon occur? Quantum mechanics suggests that particles exist in a superposition of states until they're measured. Once a measurement occurs, the entanglement collapses and both particles assume specific, predetermined values. This raises a fundamental question. How can Alice and Bob instantaneously communicate and coordinate their states? Some physicists believe that quantum entanglement suggests the existence of hidden variables or a mysterious form of instantaneous communication. On the other hand, some scientists propose a different explanation. They argue that there's no faster-than-light communication. Instead, Alice and Bob were always connected in some way, even before the initial measurement. Numerous experiments have been conducted to unravel this paradox, exploring different aspects of quantum entanglement. These studies have offered compelling evidence that the EPR paradox is a real and intriguing phenomenon. By delving into the mysteries of quantum entanglement and the EPR paradox, we're inching closer to understanding one of the most profound enigmas of our universe. The EPR paradox gives us a glimpse into the strange world of quantum mechanics. How does quantum entanglement come about? Let's delve deeper. To understand this, we need to dive into the realm of quantum mechanics, a theory that describes the behaviors of the tiniest particles in our universe. According to this theory, particles exist in a superposition of states until they are observed or measured. This means that they can be in multiple states at once, like Schrödinger's famous cat, which is simultaneously alive and dead until we open the box to check. This is where the magic of quantum entanglement begins. When two particles become entangled, their states become interlinked, forming a singular quantum system. Even when these particles are separated, they continue to exist in this superposition of states. Now, when one of these entangled particles is measured, something remarkable happens. Its state becomes determined, as per quantum mechanics. But here's the catch. The state of the other particle, no matter how far away, instantly collapses into a corresponding state. It's as if these particles are playing a perfectly coordinated dance, reacting to each other's moves in real time. This instantaneous action is what baffles scientists and contradicts our intuitive understanding of the world. We are used to events happening in a sequence, following the arrow of time. But in the quantum realm, the measurement of one particle can instantaneously determine the state of its entangled partner. This puzzling phenomenon raises a profound question. How can two particles communicate their states faster than the speed of light, seemingly breaking the universal speed limit set by Einstein's theory of relativity? The answer lies in the heart of quantum mechanics, where reality as we know it takes a back seat, and the rules of the quantum world reign supreme. Despite its counterintuitive nature, quantum entanglement has been experimentally proven, making it a cornerstone of modern physics. So there you have it, the mystery of quantum entanglement, a phenomenon that challenges our understanding of reality and takes us on a fascinating journey into the quantum realm. The measurement of one particle can instantaneously determine the state of its entangled partner. The phenomenon of quantum entanglement has sparked a great debate among physicists. As we dive into this discussion, we come across two main theories that attempt to unravel this complex mystery. The first theory involves the concept of hidden variables. This theory suggests that there are unknown factors at play, which predetermine the states of the entangled particles. These hidden variables are believed to be set at the moment of entanglement and carry the information needed to explain the correlation we observe when the particles are measured. However, this interpretation has its critics, who argue that it fails to fully capture the essence of quantum mechanics. They point out that if hidden variables existed, they would have to be non-local, meaning they could influence particles instantaneously across vast distances, a concept that fundamentally clashes with the principles of relativity. This brings us to the second theory, the idea of pre-existing connections. Proponents of this viewpoint argue that the entangled particles were always interconnected in a way that transcends traditional spatial limitations. They believe that the particles don't communicate or send information to each other when measured. Instead, they retain a deep, intrinsic link from the moment of their creation, which dictates their states when observed. This theory, while appealing for its simplicity, also faces criticism. Skeptics question how such connections could exist without violating the speed of light constraint, or how they could be maintained over large distances without any observable effects. As you can see, neither theory provides a complete and satisfactory explanation for the phenomenon of quantum entanglement. Both theories open up more questions than they answer, demonstrating the depth and complexity of the quantum world. Despite these debates, one thing remains clear. Quantum entanglement defies our classical understanding of the world and challenges us to rethink our notions of reality. The true nature of quantum entanglement remains one of the greatest enigmas in physics. As we continue to explore this intriguing phenomenon, we hope to uncover more pieces of this quantum puzzle and perhaps one day solve the mystery of quantum entanglement. Numerous experiments have been conducted to probe the bizarre nature of quantum entanglement. Unraveling the mysteries of quantum entanglement is like peeling an onion, each layer revealing a new level of complexity and intrigue. Scientists have been tirelessly conducting experiments to test the EPR paradox and the phenomenon of quantum entanglement. One of the most famous of these experiments was carried out by physicist John Bell in the 1960s. Bell's theorem was a direct challenge to Einstein's hidden variables theory. It suggested that if the universe obeys local realism, then there must be a limit to the correlation that can exist between two particles. Yet, the experiments showed correlations far beyond this limit, supporting the quantum theory. Then, there's Alain Aspect's experiments in the 1980s, which further confirmed the predictions of quantum mechanics. Aspect's experiments demonstrated that entangled particles communicate their states faster than light could travel between them. This was a stunning affirmation of quantum entanglement and a blow to local realism. Fast forward to the present day, and quantum entanglement is now being harnessed for practical applications. In the realm of quantum computing, entangled particles are used to perform complex calculations at speeds that would be impossible with classical computers. Similarly, in the field of quantum cryptography, entanglement is used to create unbreakable codes. If someone tries to intercept the information, the entanglement is broken, and the sender and receiver are alerted to the breach. These applications are just the tip of the iceberg. As we continue to probe the mysteries of quantum entanglement, who knows what other doors we may open? The experiments on quantum entanglement have not only validated the EPR paradox, but also shed light on the fundamental workings of our universe. They've shown us that reality at the quantum level is non-local and interconnected in ways we're only beginning to understand. These experiments have brought us closer to understanding the bewildering world of quantum mechanics. Quantum entanglement and the EPR paradox have deep implications for our understanding of the universe. Quantum entanglement is not just a fascinating concept, it holds the potential to revolutionize our world. It challenges the traditional laws of physics and forces us to reconsider our understanding of reality. This isn't some abstract concept confined to the realm of theoretical physics. It has practical implications, and its effects are being explored in promising fields such as quantum computing and cryptography. Consider quantum computers, a new breed of supercomputers that leverage quantum entanglement to solve complex problems at unprecedented speed. These machines could potentially outperform today's fastest supercomputers by several orders of magnitude. They could crack encryption codes, model complex biological systems, and simulate the behavior of atoms and subatomic particles with incredible precision. In the realm of quantum cryptography, quantum entanglement could be used to create a new generation of encryption systems. These systems would be virtually unbreakable, as any attempt to intercept the information would disrupt the delicate quantum state of the entangled particles and alert the sender and receiver to the intrusion. But the impact of quantum entanglement goes beyond technology. It challenges our fundamental understanding of reality. If two particles can be intimately connected regardless of the distance between them, what does that say about the nature of space and time? How does it reconcile with our understanding of causality and the speed limit of light? These are profound questions, and we don't yet have all the answers. But by studying quantum entanglement and the EPR paradox, we're starting to peel back the layers of a universe far stranger and more fascinating than we ever imagined. The journey to understand quantum entanglement is like venturing into uncharted territory. It's a thrilling expedition into the heart of reality itself. And as we delve deeper into this quantum world, we can't help but marvel at the enigma that is our universe. By unraveling the mysteries of quantum entanglement, we inch closer to unlocking the secrets of our universe. Quantum entanglement is a profound and intriguing phenomenon that continues to baffle even the brightest minds. It's a concept that feels almost magical, defying our everyday experience and understanding of reality. The essence of this paradox lies in the Einstein-Podolsky-Rosen, or EPR paradox, which illuminates the strange behavior of particles that are entangled. To put it simply, quantum entanglement is a phenomenon where particles become intertwined in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. They could be light years apart, yet they would still be connected. This strange phenomenon originates from the principles of quantum mechanics, where particles exist in a superposition of states until measured. Upon measurement, the entanglement collapses, and both particles assume predetermined states. This collapse seems to occur instantaneously, posing a significant question. How do particles communicate their states across vast distances in no time at all? This question has led to a range of theories. Some physicists suggest the existence of hidden variables or a form of faster-than-light communication. Others, however, argue that the entangled particles were always connected, even before the measurement took place. Over the decades, numerous experiments have been conducted to investigate the EPR paradox and its implications. These experiments have only confirmed the bizarre nature of quantum entanglement, demonstrating that this phenomenon is not just a theoretical construct, but a tangible aspect of our universe. And it's not just about understanding the fundamental nature of our universe. Quantum entanglement also has practical applications. It's instrumental in the development of quantum computing and cryptography, heralding a new era of technological advancements. Yet, despite all the research and the progress made, quantum entanglement remains shrouded in mystery. It continues to challenge our understanding of reality and push the boundaries of what we thought was possible. It's a testament to the enigmatic and fascinating nature of the universe we inhabit. As we delve deeper into the world of quantum physics and unravel more mysteries, we get closer to understanding the true nature of our universe. Quantum entanglement and the EPR paradox are substantial pieces of this grand puzzle, and every discovery, every revelation brings us a step closer to comprehending the intricate tapestry of our existence. Thank you for joining us on this journey into the fascinating world of quantum entanglement. Remember to subscribe for more mind-expanding content.